Hello and welcome to Unit 3. Unit 3 is Energy Transformations, and today's topic is work. All right, so what is the goal? Your learning goal today, I want you to be able to explain and calculate the value of work for real-world applications. So when we're talking about work, what are we referring to? So there are three definitions that are very important for us: energy, work, and energy transfer. So first of all, what is the definition of energy? It is the ability to do work. And I'm sure some of your parents may question your energy. Okay, maybe not that funny, but I think it's funny. So energy is the ability to do work. So what is work? Well, work is the transfer of energy. Transfer of energy. And what does that mean? So all three definitions are linked together. Energy transfer is one form of energy being converted to another. So when they ask you to take the garbage out to the end of the road for pickup, you are using your biological energy to convert it um, to motion to pick up that garbage bag and mechanical energy to move it to the end of the lane. So that is that energy transfer that we are talking about. So what are the requirements for work? So three things have to occur in order for work to occur. First one, a force must be applied. So there must be a push or a pull occurring. Second of all, the object must move. All right? If nothing moves, then you are doing no work. And the third and final important requirement, force and direction of motion must be in the same direction. The same direction. All right, so that force that's being applied, okay, that has to occur. So you have to have a force applied. You must be pushing or pulling on something. The object must move. So a lawnmower, if you're pushing on it, object must move. The only work, though, that you're really doing is the work that is in the direction of force and of movement. So those are your three requirements. Very, very important. I'm going to be right up front with you right now. These you're going to find on a test. All right. Very, very important terminology and understanding. So let's do some examples here. I got three examples on the page. A worker pushes a 20 kilogram box for 5 meters with 150 newtons. All right. So just a quick diagram. Pushes the box, 150 newtons, moves it from point A to point B, which is 5 meters. And this is the kind of the funny part here. 20 kilogram box. All right. Work, and I'm going to use energy with a W below here for work. Now the textbook is going to use just capital W for work, which is fine, but I like using E subscript W because it reminds you that work is a form of energy, okay? And it is simply, the formula is force times displacement, okay? So that is what work is. So I'm going to put a red box around that. You definitely want that on your equation sheet or cheat sheet. So now, in that formula, force times distance, mass has no role. All right, so it seems a little strange at first, but mass has no role. Okay, so 150 times 5, what's that give us? 750. 750. Now the units are forces in newtons times meters. So, just moving up here, we call that 750 joules. All right, so I'm kind of putting everything on this page right here. So Newton meters is equal to joules. And we use capital J. All right, so there you go. That is the formula when we're calculating work. Okay, next example. A child pushes a toy tractor 5 meters to the right. So the object was here at point A, now moves to point B, 5 meters to the right, 10 Newton force. How much work is done? So work is force times displacement. 10 times 5 is 50 joules. Now, you'll notice that energy doesn't need a direction. Even though we're given directions here, we are given vectors. Force is a vector, displacement's a vector. Energy is not a vector. Energy, work, are scalars, so you don't need to worry about direction. All right, they're just measuring how much work you have done. All right, so they are scalars. Okay. Now, the last one, it is I'm going to call it, you'll call it a trick question, but this is a valid question because it tests one of our 3 conditions for work. Jen's pushing her stalled car with 200 newtons of force. Car doesn't move. How much work is done? So, according to our formula, work equals force times displacement, 200 newtons. Car is not moving, so mathematically, the displacement is 0 joules. So even though she is grunting and pushing and doing with all her might trying to move her car, Jen is doing no work. All right, is doing no work. So the question is, why is she tired after doing this exercise? She'll come in exhausted because there is an energy transfer. All her muscle energy, chemical energy is being converted into a whole lot of sweating and grunting, and that's where she's really tiring herself out. So if the object does not move, there is no work being done. Okay, and it has to be in the same direction. So third and final example, and this is what, quote unquote, I'll call the hard question. So a worker pulls a cart with a force of 40 newtons, right? The handle of the cart is at a 50-degree angle. So here's my cart. This is where the worker is pulling. It's at a 50-degree angle. How much work is being done if from point A to point B, it's 20 meters? So remember the condition, okay? Force in the direction of motion. So some of that force is pulling upward on this object, all right? So the 40 newtons, there is some force pulling here. There is some force pulling here. The force in the y direction is pulling upward on the cart, and it's probably making it a bit lighter and easier to move. The force in the x direction is actually what's moving the cart, which means it's actually the amount of force in the direction of motion. So we have to find Fx. So as an aside, I'm going to do this once just to show you and then just give you the formula to work with. But we have 40 newtons. Here's my triangle, 55 degrees. I want to know the force along the bottom because it's a vector. I can find that. I know my, let's label this quickly. So hypotenuse, opposite, adjacent. I know my A and H. So that's cos. Cos theta equals A over H. I'm just going to leave it generic for the moment. My adjacent side, that is the force that I want. The hypotenuse is the force I know, which is 40. So just rearranging, multiplying both sides by 40, I get the force I'm interested in is equal to 40 cos 55. Okay, now this is the original force. That's the angle. So what does our formula become? You don't have to do this every time. I'm going to make it simple for you. So here is the formula. It is force multiplied by displacement. Well, force is just the original force, cos of the angle, cos theta, delta d. All right, so that is the formula if it's not in the same direction or horizontal. Okay, so technically you could actually just put this formula on your formula sheet, and if it's horizontal, cos of 0 degrees is always 1. So it doesn't matter which way you do it. So for this question, although it looked hard originally, it's just 40 times cos 55 times 20. It's just a matter of punching into the calculator. And I get 458.9 joules. So therefore, he did 458.9 joules of work. All right, so again, that's your, I'd call that the upper end question. And this is the formula that you need to have on the cheat sheet. You just need to add the angle in, that's the only difference. And that's it, that's your introduction to work. So again, work is those three conditions. A force must be applied, object must move, force and direction of motion have to be the same. Okay, so think of a backpack question, just as an aside here for a second. So when you go to school and you carry your new green Teenage Mutant Ninja Turtles backpack, what direction is a force acting on the backpack? Well, you could argue that you're pulling it along in this direction, but you're really not, because if you were to let go of the backpack, which way is it going to go? The force is going to pull it down, and that's due to gravity from our second unit, which means that you are holding it up. So force of u. So you're holding it up. So Fu. And what's the direction here? You've gone from point A to point B. So your direction is to the right. Your force is upward. All right, so the force you're exerting is perpendicular, so you're doing no work when you're carrying around your backpack. So you may be standing there thinking you're doing work, but carrying around your backpack is not going to do anything. So anyhow, good luck with the questions. If you have any problems, let me know.